Another type of catalysis is homogeneous catalysis. So homogeneous catalysis is where the reactants and catalysts are all in the same phase. In our case, they will be all in an aqueous solution. So we're going to look at the reaction between thiosulfate and iodide, and we're going to look at the catalyst used in this case is iron 2. So what I want you to do is to write the balance equation between the thiosulfate and iodide. So first of all, we need to know what happens to thiosulfate and what happens to iodide. So thiosulfate becomes sulfate and iodide becomes iodine. I'd strongly advise you to always balance these equations by writing the half equations. The half equations, you might spend 5 minutes or 7 minutes, or when you get quite good at it, it's very quick to balance these chemical reactions. So you feel like, oh yeah, but I've got to write 2 half equations and then combine them. But it's much quicker than trying to write the equation straight away, because you could be spending a long time without solving it. So I'm going to show you how to do these, and I strongly recommend you to practice these. So thiosulfate turns into sulfate. So first of all, you balance the atoms, if you like. So here you need to put a 2 in front of sulfate. Then all the atoms are balanced. You got 2 sulfur on each side and 8 oxygen on each side. Then you worry about the charges. So here you've got -4, and over here you've got -2. So you will need to add 2 electrons on this side. Let me put the pointer so that it's... So you need to add 2 electrons on this side. And then they're both 4-. So that half equation is now balanced. I do the same thing for iodide into iodine. So you need 2 iodine, and then you need to add, so you look at the charge, it's 2-. 2- on this side of the arrow. On this side of the arrow it's 0 because it's the element. So you will need to add 2 electrons on this side to make it the same charges. Now, to combine those 2 half equations, you need to look at the number of electrons. And if the number of electrons is not the same, so here you've got 2 plus, and here you got 2 electrons, sorry, and here you've got 2 electrons. So here in this case, you do not need to do anything other than adding them together. If those numbers are not the same, you need to find the lowest common multiple between these 2 numbers. I'm going to show you an example in a minute. So in this case, it's just a question of adding these 2 together, and the number of electrons is going to cancel each other out. So that's what happens. Because actually, as you know, in the solution, you don't have free electrons, you know, floating about. The electrons, they are carried by the reactants. Yeah, the electrons are not flowing across the solution or anything like that. So that's the equation. So from this chemical reaction, one of the questions they always ask you is, why does it have a high activation energy? And this answer can be answered by looking at the reactants. We know that for a chemical reaction to occur, you need to have collisions between the particles. Yeah? And here you can see that you need to have a collision between thiosulfate and iodide. And these 2 species are 2 negative ions. And we know that negative ions, or ions of like charges, will repel. So that's why the activation energy is really high, because they're not going to spontaneously attract each other, they're going to repel each other. So that's why the activation energy is really high. So in this case, we are going to the reaction is going to be catalyzed by iron 2+. And you can see that activation energy and that one are much lower than that one over there. So that's why the chemical reaction is going to be much faster. So it's going to go, that chemical reaction is going to occur in 2 steps, in 2 much quicker steps than the big step for the reaction between thiosulfate and iodide. So these homogeneous catalysis reactions, they require a bit of practice, to say the least, yeah, and they expect you to be able to write those equations. So we are going to look at the reaction between thiosulfate and iron 2+. So that's the half equation, yeah, thiosulfate into sulfate that we wrote on the previous slide, and iron 2+ to iron 3+. So to write the equation between thiosulfate and iron 2+, I need to combine these 2 half equations. And you can see here that you've got 2 electrons, and here you've got 1. So you need to find the lowest common multiple. So you need to multiply this one by 2. And then when I add those 2 together, you can see you've got 2 electrons on that side of the arrow, and then 2 electrons on the other side of the arrow. So they cancel each other out. And that's the reaction between thiosulfate and iron 2+. So that's your first reaction, right? Then iron 3+ is going to be reduced by iodide, and iron 2+ is going to be regenerated. That's why overall you'll start with Fe2+, it turns into Fe3+, and then Fe3+ turns again into Fe2+. So overall it's not being used up. But let's demonstrate this. So now I'm going to write the equation of the reaction between iron 3+ and iodide. So iron 3+ is going to turn to Fe2+ by gaining an electron, by being reduced, and iodide is going to be oxidized by losing 2 electrons. So here I have 1 electron and 2 electrons, so I will need to multiply also this one by 2 to combine the 2 together. So you can see that overall thiosulfate has turned into sulfate, iodide has been oxidized to iodine. Yeah, iodide has lost electrons, and our catalyst truly is a catalyst, because iron 2+ is iron 2+ here, and it's still iron 2+ there. So it hasn't changed, it hasn't been used up. Yeah, it hasn't been oxidized or reduced. Temporarily, yes, but overall it hasn't. So this is a classic example that they ask about frequently. So they do require a little bit of work, to say the least. Another example of homogeneous catalysis is autocatalysis. So the definition of autocatalysis is when one of the products is the catalyst of the reaction. Okay, autocatalysis, the catalyst is a product of the chemical reaction. An example is the reaction between manganate, MnO4-, and ethane dioate, or also known as oxalate. So that is a common ligand, bidentate ligand, and that's a very, very common oxidizing agent. So what we need to know from this, when you see MnO4-, you need to know that they get reduced to Mn2+, and that oxalate gets, I made a mistake, sorry, they get oxidized to CO2. So apologies for that, that should read oxidized. So let's write the reaction, the equation for the reaction between manganate and oxalate ions. So I am only going to be able to do this really by writing the two half equations. Yeah? Otherwise I could be spending a long time and not solve it at all. So a common half equation, Mn4 minus into Mn2 plus. So how to do this? You see here you've got 4 oxygen atoms. Oh, first of all, apologies, you need to look. I've got 1 Mn and 1 Mn, so that's fine, that's balanced. Then I balance the oxygen atoms. I've got 4 here, so I'm going to add 4 water. Then to balance the hydrogen atoms, I need to add protons on the other side, H+. That's why these chemical reactions, they are always done in acidic conditions. So they are done in acidic conditions to provide those protons. And then, now that the atoms, if you like, for better words, that are balanced, I need to balance the charges. So on this side, I've got 2 plus. And on this side, I've got 7 plus. So to make it the same, I need to add 5 electrons on this side, so make it 2 plus overall. Okay? So that's your half equation balanced. Do the same with ethane dioxide to carbon dioxide. So here you can see that you need to multiply this one by 2. You look at the charges, it's 2 minus, and here is 0. So you'll need to add 2 electrons on this side to make it 2 minus. Now I'm going to look at the electrons. So I've got 5 on this side, 2 on that side. So the lowest common multiple is 10, so I will need to multiply this one by 2 and that one by 5. Multiply that one by 2 and the bottom one by 5. And by combining them, the number of electrons, you will have 10 on that side. You'll have 10 on that side, they cancel out with the 10 on the other side. So that's the reaction between manganate and oxalate. And you can see that that reaction is going to be quite tricky, because here you also have 2 negative ions, and because they've got the same charge, they will repel, so that will have a high activation energy. And we're going to show that Mn2 plus is the catalyst of that chemical reaction. So Mn2 plus is a product but also catalyzes that chemical reaction. That's why we call this an autocatalytic reaction, yeah, where the product or one of the products is the catalyst. So I am going to show the reaction between manganate and Mn2 plus. So manganate turns into Mn2 plus. Okay, so I balance the same the equation the same way as I did for the previous slide. Okay, Mn2 plus, that's going to react with this, turns into Mn3 plus. So you add 1 electron. Then you look at the lowest common multiple, which is 5. So the bottom one, this one is going to be multiplied by 5. Then I combine the two reactions. So Mn4 minus reacts with Mn2 plus to form Mn3 plus. And then you can see that this one is going to be a favored reaction, because you've got a negative ion and a positive ion reacting together. And that's very feasible, because they will attract each other because they've got opposite charges. Now, this one is going to react with our other negative ion. So that's your ethane dioxide into carbon dioxide. So we've already balanced that chemical reaction from on the previous slide. And same here. So I've got 1 electron and 2 electrons, so the lowest common multiple is 2, so I will need to multiply this one by 2. And I combine the two. Okay, so here I have MnO4 minus that turns into Mn3 plus. Okay, and then your catalyst Mn3 plus turns into Mn2 plus, so it's regenerated. So that's why the catalyst is Mn2 plus and also a product of that chemical reaction. So that does take a little bit of time to get your head around, I must admit, but these equations, they expect you to know them. So then they often ask you to sketch the concentration of MnO4 minus, the change in concentration of MnO4 minus over time. So at the beginning, that concentration of MnO4 minus, well, it's not going to change very much, because it's going to be, the chemical reaction will have a very slow rate of reaction, because you've got MnO4 minus and C2O4 minus trying to combine, and these two they have opposite charges. Yeah, so that chemical reactions will take a while to take place. Yeah, because you got two negative ions. But as soon as some of Mn2 plus is formed, then the rate of reaction is going to increase, because it's going to act as the catalyst. So you have those two reactions coming on. Yeah, Mn2 plus turns to Mn3 plus. Mn3 plus reacts with oxalate to form Mn2 plus. So the rate of reaction increases because the concentration of the catalyst increases. More products are made, more catalysts are made, more catalysts are made, more products are made, until you run out of reactants. Okay, so that's the profile. Thank you.